Hello and welcome back again. In this video, we're going to expand on what we've already learned about binary. So in the first two videos, we explored basics of binary math, and then binary math and applying it to a decimal value. In this video, we're going to apply this now to a value called hexadecimal. Hexadecimal is a way that we represent values between 0 and 15 using the numbers 0 through 9 and the letters A through F. What this does, this allows us to condense a lot of information into a very, very tight format. It also allows us to represent most things in a binary format fairly easily. So where we use it in networking, in the late 90s, they realized that IPv4 addressing was not going to work out long term. There was just not enough addresses to go around. So they decided to develop a whole new address scheme. Instead of going with 64-bit addresses, they decided to double it and go to 128-bit addresses. So IPv4, 32-bit addresses, right? There have been 32 binary values. With IPv6, we have 128 binary values, 128 bits. What this essentially does, there are enough addresses available in IPv6, we could take every star in the sky with every planet they have and assign them their own network and still never run out of addresses. It's absolutely mind-boggling how many addresses there are. With IPv6, though, we work in a address scheme that's 4 times greater than IPv4. As a result, we didn't want to have 4 times the data in a address, right? As far as 4 times the inputs to put in. So what we did instead, we started working with hexadecimal. Hexadecimal allows us to have a much smaller chunk of information. Instead of working in 8 bits, we're going to work in 4. A nibble, as we talked in other videos. We're going to convert that 4-bit nibble into a letter or a number. Each hexadecimal character represents one of 16 possible values. So let's look at how that works. All right. So the binary grid for nibble would start at 1, 2, 4, 8. And it stops right there because we only have 4 bits, 1, 2, 4, 8. The goal of hexadecimal is to represent any combination of those bits being turned on with only using a single character. So if you could only press one key on your keyboard to represent any of the combinations here, how do you do it? Now, if you do the math, you're going to say, well, anything 1 through 9 of totals is easy, but when we get to 10, how do you represent 10 on a keyboard with only one character? And the way we do that is we then switch to letters, A through F. So let's look at some here. So 0 to 9, easy, right? 1, for representing this combo, 1, 0, 0, 1. 8 plus 1 is 9. One press of the button, no problem. 0, 1, 1, 1. Easy. 7. 4, 2, 1. Totals to 7. 1, 0, 0, 0. Okay, value of 8. 0, 0, 1, 1. Value of 3. But when we move in above that, we go through 10 to 15, we have to be able to represent it in another manner. So what we do is we switch then to A through F. So 10 is represented by the letter A. Again, a single press. Our goal is to represent the number with only one character. 11, B, 12, C, 13, D, 14, E, 15, F. So the full grid for hexadecimal looks like this. We can see our assorted binary values of 0 through 9, just like we would expect. And then when we move to 10, we switch to A so that we can fit it within a single character value. So a common IPv6 address would look something like that up top. Each hex character represents 16 possible values. All right? And if each character represents 16 possible values, then the above address, right, has 16 values in the last character alone. In just that number 1, there are 16 possible values there. So, the next value in this set would be same address with 0012 at the end. The last value in that set would be 001F. Okay? Because that would be the 16th value. A total of 15, right? 0 is a value, so the last value would be F. The very next number we would have to use would be 0020 in that last hextet. These are called hextets. Any of these 4-digit or 4-character values are called hextets. But we would go to 020 and then 021, 022, 023, all the way through 02F and then 0030. Okay? So when we get into talking more about addressing in depth, we're going to talk about the concept of buckets. And we'll talk about this during class on Tuesday. With binary and how binary flows, it's a bucket within a buckets within buckets within buckets. That everything has to flow from right to left. And as you run out of space in a bucket, you have to pour it into the next one, but that empties that bucket back out. Okay? We will talk about it in length. I believe I talked about it during the Binary Math Basics video, but we're going to actually talk about this concept at length in class on Tuesday. But what this overall means for IPv6 and hexadecimal, every time you move characters from right to left, you have 16 values, and that's 16 values to the power of however many places you can move. So if you are moving 4 characters, that's 16 to the 4th power. With just 2 characters, we have 256 possible combinations, 16 times 16. With 3 characters, we have 4,096 possible combinations of zeros and ones in just 3 characters. Okay? 16 times 16 times 16. With an entire hextet with just 4 characters. So if we look at it and say just these last 4 characters, with the total values that we could put in there, there are 65,536 different combinations represented in just 4 characters. Okay? And that's only one of 8 chunks in an IPv6 address. It gets nutty. So, let's look at just that last hextet, okay, that last chunk, and let's take it to binary. This one's pretty easy, right? So 0011. So how do we represent 0 in binary in a nibble? Well, these would all be zeros. Same thing for the next one. How do we represent 1? Well, can we subtract 8 from 1? No, so it's off. 4 from 1? No, it's off. 2 from 1? No, it's off. 1 from 1? 1. Yes, it's on. So we would turn this on. And the same thing on the next row. Our end result looks like this. And when we put that string together, 0011 can get represented in this 16-bit string. Okay? But in this string, in this 16-bit string, there are 65,536 total combinations of zeros and ones that we could put into that string. All right? So the next host address in that chunk would be 0012. Why don't you work to see if you can figure out the binary for it? And then also go ahead and work through the binary for each of the following host chunks. Pause the video and do that now. All right, assuming you pause the video and you're coming back to it now, you should have gotten the following results. And you can pause and validate your numbers. Now, the last question for 001F said, what would the next value be? If you answered 0020, you're right. And then after that, 0021. But when we talked about buckets, let's look at what that looks like. As we count in binary, and we do math in binary, we can do math right to left, or left to right. We do our subtraction left to right. But as binary counts up in value, it always works from the right to the left. And what happens is, so for example, let's look at 0013. Or actually, we can look at 0012. So the representation for 0012, let's ignore all these zeros to start with. And let's just look at starting with what actually has populated value. That 1000. For the next value up, what we're going to do is we're going to look at from the right where the first unfilled value is. All right? Well, in this case, the first unfilled value is the 1 bit. The 1 bit. So we're going to turn that on. When we turn that on, now we are at all the zeros, 10011. This is a value of, in hexadecimal, 0013. Where this chunk represents 0, the first 0. These 4 represent the second 0. These 4 represent a value of 1. And these 4 at the end represent a value of 3. Now, since we're counting up and we're only really working in the last character for right now, we can just look at those last 4. But what happens? We look and we say, okay, well, we need to count up in our next available empty spot, in our next available empty unfilled bit. So if we looked, we ended with 1s, so our next unfilled bit is this third one from the right. So what we would do is we would turn this bit on, but this is where that buckets within buckets concept comes in. Because this bit turns on, the bits after it to the right have to turn off. Okay? So basically we're going to take everything that's in these 2 buckets, and we need to add 1 more to it, but the buckets are full. So we're going to pour everything into the next bucket over. Let's go through that again. We want to add another value to these 2 positives, these 2 bits that are on, but since they're full, we don't have anywhere to add them. So what we're going to do, we're going to pour all of it over into the next bucket bigger. So it pours in, and away we go. And look at it like this. These 2 have a value total of 3, right? You have your 1 value and your 2 value, totals to 3. In order to get a value of 4, we have to go to the next bit to represent it. So we add 1, and everything pours in, and it empties out these 2. The next one up, for a value of 5, where's our first empty bit from the right? Well, the first empty bit from the right is the first one with a value of 1. So we represent 5 as 0, 1, 0, 1. When we want to go to 6, where's our first empty bit from the right? Oh, okay. The first empty bit from the right is the 2 value. The 1's already full, so we're going to have to fill the 2 and empty the 1. And now we can see the values of 2 and 4 are populated, giving us a total value of 6. 7, the first empty one is the 1 value. We fill it, and we have 0, 0, 1, 1, 1. When we want to go to 8, what's going to happen? These are full. So everything pours over, and we would have a value of 1, 0, 0, 0. 9, 1, 0, 0, 1. 10 would be 1, 0, 1, 0. 11, 1, 0, 1, 1. Etc., so on and so forth. When we get to the part where all of those are 1s, right? We represent, that's 15, and we represent that with the letter F. That's the end. That's as full as this bucket could get. So what happens is, for the next value up, where's our first 0? And we see, oh, okay, well, in these 4 here, if I can get my cursor right, we were 0, 0, 0, 1. So the second character from the right was a 1. And where's our first 0? Oh, it's here. So what happens? We have to pour the buckets over. This becomes we change our second location to a 1 and our first bit value to a 0 to give us a value of 0, 2, 0. But now as we continue to count up, right, because we were completely full, as we continue to count up, now we are going to do this all the way from 0, 2, 0 to 0, 2, F. And then we'll get 0, 3, 0. And we're going to do it all again from 0, 3, 0 to 0, 3, F. And then we're going to go all the way to 0, 4, 0. So you try to wrap your head around how that's counting up. The common mistake I see a lot of students make is they try to do, oh, okay, well, 0, 1, F. Well, then it's 0, 2, F. Because they disconnect the buckets too thoroughly. Because this is a solid string, it's always going to count that way. All right? So, a full IPv6 address in binary is going to be 128 characters long. That's 128 presses of 0 or 1 for a full one. So for the address 2600 32AF B7 Delta Echo 888813 FE 1234 ABCD 011 in binary looks like this massive 128 character string. It's just absolutely nutty. When we get closer into IPv6 addressing and talking about it, we'll talk about how we split this address up and how we use it for subnetting and those things. But it's important for you to understand how to take the binary of either decimal with octets and 8-bit values or hexadecimal with 4-bit values and work those into your addresses to understand how many addresses you get in any system. All right? So next steps. I want you to practice decimal and hexadecimal to binary and back. I want you to just pick random numbers and write them out, or do a random bit of eight pieces of binary, or 4-bit chunk, or even a 16-bit chunk and switch it to hexadecimal. When you're really good at it, when you feel like you got a good grasp, You're going to complete the binary and hexadecimal assignment. It's in Canvas in Module Week 1. Don't complete the assignment before we have class on Tuesday. On Tuesday, what we're going to do, we'll spend some time going through and discussing this concept and practicing binary, decimal, and hexadecimal before you launch into this homework. As always, if you need absolutely anything, reach out on one of the channels that have been established to get a hold of me, and I will be happy to answer your questions. Thanks, and have a great one.